So each time this type of conference, I am very astonished by the amount of things known about. Yeah, so there is a lot of things known about infinite sequences, and what is strange for me is that people do not pay equal attention to finite sequences, finite strings, and even very simple things about finite strings are not well understood. So today I'll try to give some example of a very strange kind of proof which use some, not to say, very simple homotopy theory, but for very basic question. So there is a theorem, statement first proved by Misha Vyugin, and the statement is like this. We have some string x, and we want to find some y such that the distance, information distance in both directions is given, is equal to some prescribed values. For example, we want to find given x, we want to find y such that complexity of this is n plus constant, and complexity of y given x is n plus constant. And the question whether it's possible or not. And of course, as you can see immediately from the statement, it's not always possible, because if x is simple itself, then of course it cannot have high complexity given y. So we need to know that if we need to assume something about C of x. And what Vyugin proved was that if complexity of x is greater than 2n plus constant, then for every x, if the complexity of x is big enough, then such y exists. So you can find always y on the distance in both directions. And what I will explain today is that actually this is too strong condition, and you can use almost the minimal one, which is n plus O of log n. So you can improve the result and with smaller bound. So it's close to optimal. But what is very strange is it's not that the statement is maybe not that interesting, because we are very precise in our complexity. But what is strange and funny is the how it's proved. So actually things are like this. So we know that if there is 0, we know here is n, here is 2n, and we know that if complexity is greater than 2n, then there is a Vyugin argument which use some game. I think that we will discuss this argument later. But there is completely different argument which can be applied for some n starting from n to actually any polynomial of n. So actually it should be O of log n here. So what is funny that we have two different arguments. Each of them covers some range of complexities of x. But one can be applied if complexity is greater than 2n, and another one can be applied if it's greater than n, but not very big. So together they are enough for cover the entire thing, but still none of them separately does the job. So it's already a bit strange. And even what is more strange is how this kind of topological argument. And I can tell you what kind of what kind of topology, simple topology, we'll use. So there is a theorem which says that imagine we have a circle and we have a mapping of the circle somewhere, mapping to the plane, mapping of f of S1 to R2. And imagine that this path makes a non-zero number of rounds, turns around some point O. The index, this formally you should consider the mapping of the sphere to the plane without the point, and then there is a homotopy fundamental group which is Z, and so this mapping should represent a non-zero element in this fundamental group. But it's all we need just to intuitively understand the notion of turns. So now here it makes 2, but any non-zero number will work. And non-zero number of turns. And if it's the case, then every extension of this mapping to D2, if we extend this continuous mapping into an entire disk, then we cannot avoid this point. Then definitely some points here will be mapped into O. Because just how it's proved. Just let's start looking at smaller and smaller things and see how they are mapped. So there are kind of paths there, and at the end we have just one point. So we can look how many turns the image does when we move around a circle of variable size. So here we have this non-zero number of turns, and at the end, since we are in the one point, we have a zero number. So at some point the number should change, and the only way to change is to cross this point. So formally you can say that this is it's just a homotopy between this path and the constant path, and so if the element is non-zero, then such a homotopy cannot exist. So this is topological, very simple topological fact, but what is not clear how we can use it. And but we can do it in a rather simple way. Let's first concentrate on a kind of modal example. Imagine we want to have only one thing. So we have some x. We know that complexity of x is greater than n. And we want to find y such that complexity of x given y is exactly n. Of course, with constant precision, which is unavoidable here. So just in one direction. So what do we do? Why it exists? So what should you do?
I know.
Yeah, but probably everybody knows. So okay, just say it.
We take two extreme cases, y is empty and y is equal to x.
Yeah,
Extreme
so
cases.
if y is empty, this is of course something greater than n. And when y is equal to x, then it's constant. Yeah.
And then we draw, so say, a path. I mean, we change x bit by bit, say, just erasing bits from the...
And there is a continuous, but kind of discretely continuous path between two things. We can just erase bit by bit from y until it becomes empty. And each stage, the complexity changes only by a constant. So if we add one bit, we can change the complexity only by a constant thing. So there is a kind of intermediate value theorem. We have something greater than n, and at the end we have something 0, and so we should cross exactly n at some point. So it seems like kind of trivial thing, but just a bit more complicated version of this argument will give us our statement. And let me explain how it happens. But first, so for training, let's consider another problem. Imagine we want to have these things. Now we want to have both things, but with a bit smaller precision of log n. So now we want to find something on information distance n plus O of log n, and which is much more actual, to say the truth, it's much more natural question. Because, for example, if we're looking at this question, we should be sure that we really want plain complexity, not prefix 1. And here it's much more invariant and much more natural. One can doubt whether exact value of complexity is so important. But and indeed, this argument is, in this case, is very simple. So what we should do, we should take x, and first we should replace it by an incompressible string. So let p be the shortest program for x. And now we know that, of course, we can get x from p with a constant amount of information, and also we can get p from x with logarithmically logarithm of complexity of x. So now we assume that complexity is polynomial in n, so it's not important whether we have complexity or n here. So first step is that we replace with our precision. We can assume without loss of generality that x is actually incompressible. We replace it, and p is then incompressible. So what should we do then? So if we need something, if we need y to have complexity n, so we need to add n new bits. So we take some q of size n and independent of p. The mutual information between p and q is very small. And then we take this p, which is longer than n, and we just take q and replace part of p by q. So we take things like this. So here is our y. So we delete n bits of p and replace them by some new fresh n bits. So it's more or less obvious that both things are okay. So this is a low precision thing. And then the question is, how can we combine all these tools to get the desired high precision thing? But I think more or less now it is not difficult to imagine how to do this, but let me do it. So we start like this. So we have a c, we have x, which complexity is between n plus O of log n, and polynomial of n. And we switch to P, which is shortest program for x. And also we take some Q, which will be used as a source of new bits. But let's try a random independent from P string of size 2n. So we have again the same P, which has the bits from x, and some fresh bits with some a bit more than we need. And what we want to know to get is just we will look from y among the strings obtained in the same way. We take two numbers and take k first bits of P and L first bits of Q. And my claim is that for suitable values of K and L, we will get whatever we want. So we use the same trick, but what we need, where we need to be more careful, is just we need to adjust the size of these things a bit, and then we can get the precision we want. So for some K and L, this works. Okay, so why it works? And here is a place when we need to consider a mapping, a continuous mapping like this. So you may guess what is this mapping. So K runs between, we take bits of P, so it runs between 0 and complexity of x. And L runs between 0 and 2n. So this is L, this is K. So for every point KL in this rectangle, we have some string YKL. And then this string can be checked whether it's okay for us or not. For this, we consider another plane where is the complexity of x given y and complexity of y given x. So we have some point here, which is complexity of x given YKL and complexity of YKL given x. Again, the complexity of x given y can be between 0 and complexity of x, and complexity of y given x is somewhere between 0 and complexity of y. So we have this, the same rectangle. And what we need to show that this mappings covers the point NN. So this is the point we want to achieve, and so if for some K and L we get this O of 1 close to NN, that's all we want. And now we are exactly in this in the discrete framework like this. So let's look what happens, how the image moves if we move our point here. So what we imagine, we move from A, make this path A, B, C, D. And let's see what we get on the other side. So A means that K and L are 0, so Y is actually empty, no information. So the complexity of Y is 0, and so we are on this line, and the complexity of X given Y is just complexity of X. So A moved here, so the image of A is here. For trivial reasons. Now what we do, we increase the p's taken from P, we increase K, which is taken from P, so we get more and more bits of program for X. And we still don't use this Q thing. So we have just essentially here X, this Y is a prefix not of X but of its shortest program, prefix of P. So what happens? Complexity of Y given X is small because Y is a prefix of X. So the only thing we need to specify additionally is the length. So its complexity is logarithmic here. So we are inside this logarithm thing. But when we add, when K is entire, this K is here, when we get the entire program. So complexity of program given X is logarithmic, and complexity of X given program is just a constant. So we are somewhere here. So this B is B prime. And you may guess what is happening then. Then when we go from B to C, we start adding random bits to our Y. So Y is now a complete program for X plus some random bits. So still we have the complexity of X given Y is 0, and the complexity of Y given X increases now because of this random bits. At the end, it becomes 2n, because we assume that Q are independent of P, so even we know P or X is more or less the same with logarithmic precision. So we come to this point. And this is C. And then we start to delete the parts which corresponds to X, and only when we move to D, only the random points are random bits remain. So in this case, both complexities are maximal. So I hope you more or less believe me that if whatever we do, we just make the round turn in some logarithmic zone of this thing. So it's O of log n. So that's all, because now we have, if we make the turn, we make one turn here in the negative direction. So it's impossible that we miss always the point, and it should be in the image of this mapping. So if you need to say it formally, you can either you can formulate the discrete version of this homotopy thing, or you can just use classical theorem as a result without going into the proof. So we have a mapping which is actually defined on a grid, but we may make it continuous mapping of the entire rectangle just by making a linear interpolation on every triangle. So we get some continuous mapping of the entire rectangle, which makes a turn when we go like this. So there should be some preimage. Now it may be not integer, but it is inside some triangle. And we know that the values of x, of complexities, this mapping again is continuous. If we change one, we add or delete one bit, the complexity change only by a constant. So all three things are mapped in some, almost in the same place. And all the points inside are mapped also in the triangle here. So all these points should be close to n. So this is the end of the proof, and I hope you agree that nothing really happens here. It's just kind of mystical, trivial continuity thing. And but it would not be such a strange thing in itself, and indeed you can prove other things using this computable topological argument. So let me formulate another. So for example, there is an open question. It's kind of a shame for us that this question seems to be open. So imagine we have any strings a and b. For every a and b, there exists some oracle, some string actually, not oracle in classical sense, some string c, which halves their complexity. So the complexity of a given c is exactly 1/2 of complexity of a, and complexity of b given c is 1/2 of complexity of b. Or maybe it's better to write some u, because c will be. So it looks very natural somehow, but it's not clear how to prove this. But with topology argument, you can prove that with additional conditional, if a and b are almost independent, so the mutual information in a and b is much less than complexity of a and complexity of b, then you can indeed find such a thing. And I hope that this argument is intuitive enough so you can imagine what kind of mapping we need to consider here. So how should we find this u? In which class we should look for it? And so it should contain some information about a and b. So what we could do, the only reasonable thing to do is just to take a program P for A, take a shortest program for B, and then take U KL, which is K bits of P and L bits of Q.
Why do we start with the shortest programs for A and B?
Instead of A, why this strange thing?
Instead of A and B
themselves.
Yeah.
This is here is the problem. Imagine that X is very long. X is extremely, say it's a string of zeros with some length, and the length really contains all the information. Then if we take k first bits of P, on the way we will encounter many different k's, and some of them will be very informative in length. just the length will be, the length of this thing will contain a lot of information about y. So our hope, here what we needed to know that we are still in this small region. So we get around this point. And if x is very large, then the length is no more bounded, and we get a trouble here.
But look, anyway, you have this assumption that the complexity of x is small.
Yeah, the complexity, but not the length. No, if I know that the length is small, then we can, of course, use this as just the x itself. So it's just a way of getting rid of this. Okay, so here we do the same thing, and we consider the mapping, and it goes around the point, and so it should cover the point, every point in the rectangle. For example, the center of the rectangle. Of course, this theorem, this 1/2 is just an example of our inability to solve even the simplest problem. So we have this very nothing special in 1/2. And also, if we want to consider 3 strings. Formation, yeah, because we want to know the behavior of this function, of C of A given UKL and C of B given UKL. So if A and B are almost independent, then the behavior of these things are predictable. We have K bits of A, and we know what does it mean. And we have L bits of B, which are not related to A. So we know that this complexity is more or less the remaining thing. So it's more or less complexity of A minus K with logarithmic precision. And this is complexity of B minus L with logarithmic precision. So we know the behavior of the thing.
Then why not to solve that equation? Just write that C of A minus K equals 1/2.
Yeah, because then we can solve this equation. This is with logarithmic precision.
I see.
And so this is the point. So if we want to do this with logarithmic precision, as everything is more or less trivial, we take as you know, at least if they are independent. If they are dependent, it's another story. But also there is a very clever trick. This is all trivial, but Andrei Ramashchenko looked at this and invented a much less trivial argument, saying that we can assume that they are not we don't need them to be independent. We can use some Muchnik technique with this conditional codes to be in the case when A and B are not exactly the same. So the complexities of A given B and complexity of B given A should not be negligible. So there should be something different, a bit different in them. And then it's enough to prove that there exists a U which halves makes the information twice smaller. But this is for 2 strings, actually. But what was funny for 3 strings, that here we need to use more advanced topology. There's not, if you need to motivate the study of topology, why you need to solve, to know what is a homotopy group of higher order and what is the, why they are useful. This is the answer. You can prove that you can halve the complexity of 3 or 4 strings. Probably in this building, people will kill us for this argument. But still for logicians, even this argument could be convincing. Again, we get here a mapping not of a rectangle, but of a square, of a box, and we know how it behaves on the boundary of the box, and it goes around some point. So if we extend it on the interior of the box, we should cover all the points inside the box. So this is topology is the same, but more dimensions. Okay, so this is about topological part, and then to make explain why it's so strange, I would like to present the original argument for this part. So here is a kind of game argument. It's only a nice, funny game, but what is very strange is it has no resemblance to the topological argument at all, completely different. And so this is why the challenge for you is to invent something which will cover the entire range. Now you will see two simple arguments for different parts, but then one argument for the entire thing should be needed. So let me explain the game argument of Eugen. Actually, to be more simple, since for us it's the same, we cover this zone anyway, let's start with 3n instead of 2n. There is some simplification for 3n. It becomes much easier. But still it doesn't, there is no way to adapt this algorithm for n, at least. And so let's, it's very dangerous analogy, but let's see that there's a game or strategy for a dating agency. And I will try to explain what is a dating agency job, why it's enough to prove the theorem, and how to achieve this job. So dating agency start as usual with some matching. But we assume that there are some two countable sets, x and y. Countable. They are just sets of binary strings, for example. And we start with some initial matching. For example, we can start with identity matching. And for a while, everybody is happy. But then people start to complain. So each person can, it's not even complain, send a refusal. So a person from X can say that, no, I don't like this. And a person of Y can say, no, I don't like this. And then whatever, it's enough for one of them to be unhappy, then this pair is dissolved. And so if they are just dissolved, we get more and more free vertices on the left and the right. And but there is some limitation. At most, less than n refusals allowed for each person. So, of course, a person can be refused many times. It's outside its control. But there is another thing, that the refusal made by the person should be bounded. You should not be too picky. Otherwise the agency cannot do the job. And then what is allowed to do for agency? They can make they can create new pairs from free elements. And actually, this is an unfair dating agency, which cares more about people in X. And so what dating agencies should do, if somebody in X is now becomes free, there are two possibilities for free elements of X. Either you should find a new pair immediately, or you can, instead of finding a new pair, declare this element to be hopeless. So if, it's unavoidable at some time, you can say, okay, it's not possible to do anything, and then you forget, dating agency should forget about this person.
Sasha,
Yeah.
an element has refused some other element, it can never be paired with that same element again?
Yeah, of course. No change of mind, it's too complicated. Now, if the new element, a new pair should also only be with the element which was never tried with. And so, what are the obligations of dating agency? First, there are two of them, quantitative one. So, each person has at most 2n attempts. So nobody should be tried with more than 2n different pairs. And we should limit the amount of hopeless people. So at most, actually O of n cube hopeless people. Kind of also, this n cube corresponds actually to 3n, as you will guess. So that's all, and the lemma says that there exists a computable strategy for the agency. So agency can do the job. And it's quite clear, let me explain why it's enough to prove the theorem. So how we apply this to our case. So x and y are binary strings. And x, u refuses v if complexity of v given u is less than n. And each person then can refuse at most n big, which is 2 to the n elements. So a person doesn't want to be matched to somebody who is very simple with respect to this person. That makes life not interesting enough. So you need to have a complicated partner here. So this is the only this specifies the behavior of all people. They just try all the programs, and when they find a short program, they see that the complexity is less than n. They refuse. Of course, they look on the program for the current partner. So if they find that the partner is simple, then they send a refusal. And so let's see. So there are O of 2 to the 3n hopeless people. And they are enumerated. In the process, they are declared as hopeless explicitly. So each of them can be described by the number in this said list. So each hopeless has complexity less than 3n plus constant. And for all other people, for all strings which have complexity more than 3n, other x, not hopeless, there is a final partner. Since there are only finitely many attempts, there is a final partner y. And we know that since there was no rejection, we know that complexity in both directions is at least n. Otherwise, at some point, they will reject each other. And on the other hand, this complexity is bounded by n plus O of 1, because each of them, known, for example, when x known, y is determined by the ordinal number in the list of x partners. So you just say that the third husband of x. So you see that, and this number is bounded by 2n. So it's log 2 to the n plus 1 bits. Okay, so what I now think that I described the game and I explained how this game can be used to prove the theorem. And what is not explained and what I'll try to explain now, how to win the game, what the agency should do. But what I hope that this part is more or less clear. So, okay, if you agree, I can.
Minimum size for x and y, so that the lemma is true in this form.
So say it.
Relative to large n, how big do x and y the sets have to be for the lemma itself?
Oh no, we consider countable x and y. So we just infinite. No, probably we can use the same thing for finitely. But if they are smaller than n cubed, then that's no problem. We can just say that everybody is hopeless. But if they are large enough, then we can apply the same trick, and it doesn't matter. So the question is what the data agency should do. And there is the main problem which we need to solve here is the problem of course any person can refuse at most n person, that's okay. But the question is whether the person will be refused by much more. And this is the main idea, which is quite natural if you think a bit, that if we have a new person which was rejected many times already, and we look for a pair, the pair should be another person who already sent a lot of rejections, because then he is less chances to get a new rejection. So the idea is that there should be some matching in the life experience of the people. So let me say what the strategy is. So each person remembers two numbers of rejection sent and the shameful number of rejection received. And originally all them have zero, pair zero, nobody. And then imagine that, for example, this person starts to reject this one. So we get matching pair. There is one rejection sent here and one rejection received here. And they become free both. At that point, the agency has nothing, cannot do anything, because there's only one free person, and this free person is unavailable. But when something happens like this again, we can find, for example, somebody has the same thing, and maybe the third person, the rejection goes another direction. We have here 0, 1, and here, so this is broken. And so the idea is that we match a new pair, we construct a new pair if there are people with the same, with matching experience. So since this guy also has one rejection sent, one received and no sent, and here is one sent and no received, we say that they are matching situations.
Not completely matching. So that number number of rejections sent should be equal to the number of rejections.
Yeah. They are not okay. Maybe we should write the numbers in a better way. This number of send left to right and send right to left, so they can completely identify them. But in terms of our analogy, we should match. If the person has already sent a lot of rejections, he should be matched to the person who received exactly the same number of rejections and sent exactly the same number of rejections as find, I would say in very general terms, but a pair with matching experience. Yeah.
So if you do this, then you're likely that, I mean, if an element has sent many rejections, that probably means that it's quite complicated relative to other elements. And if another element has already received lots of rejections, then it's probably because it's too easy. So if you do this strategy, isn't it very likely that the new element will be rejected again?
No. No, you want to say how it will work in our specific case of complexities. Yeah, but no, I don't know how.
Okay.
Just it works.
Okay.
But in this terms, I should think how to explain why it's not
I just
paradoxical.
mean if we have two elements that both have sent many rejections, because they both have high complexity, so it would, I don't know, from a strategy point of view, it would seem more natural to pair those.
Yeah.
And not one that is probably very complicated with one that's probably very easy. So that's why it confuses me. But okay, I mean, if it works.
No, but it's not just complex, but contains a lot of information about the former partners. It's not exactly complexity. Okay, but let me just say why it works. It's very simple. So find a pair with matching experience, and if such a pair, such element doesn't exist, just declare hopeless. So very simple strategy. If you can find the person with the same experience, do this. If not, do nothing, and still you get a pool of you have a pool of hopeless elements on one side on X, and you have a pool of free elements on the other side. And of course, since we always the things are matching, the number of free elements and number of hopeless elements are the same, and their classification according to these experiences are also the same, because always we make pairs and destroy pairs, that we move the experience indices in the same way. And then it's we need to bound the number of hopeless element. So hopeless element, now what is important, and what I tried to explain, that now both things in all the elements are less than n, because if things are matching, then the number of received refusals is the number of sent on the other side, so it cannot be more than n. So the experience is a pair of two numbers, and so it's n squared possible experience. So there are n squared classes, and each class contains at most 2n elements. So this will get n cube bound. And the reason is simple. Imagine the class cannot become, imagine it already reached 2n elements. Then if we have a new person appearing in this class, and we have already 2n possible pairs with this person, and the pairs which are not allowed, these are the pairs which were already tried. And we can have less than 2n previous less than 2n changes. Because at each time one of the numbers increases. So when there are more than 2n, when there is 2n free elements, then the choice is enough always to find a fresh, relatively fresh partner for x. So each class remains bounded, the number of classes is bounded, we get n's cubed, and that's finished the argument. And so you again get this thing which now it can work without, we don't need this restriction of poly of n. Of course x, now the complexity of x can be as large as we want, and still everything works. And the challenge is how to combine these two funny arguments in one which is simple and intuitive. The statements are overlapping in a very natural way, so it should be one argument which covers all the region. But this is what I don't know how to do. And also the final remark I would like to make, since we are in the Newton Institute, there is another possible approach to this, but which I don't know whether does it have any sense or not. So imagine that we have some y when the things are close to n. And so there is a Newton approximation method. We can just try to change x in some direction and see how this both number change, and change in other direction, and try some combination of these two directions, and maybe we can just it's like in Newton metaphor. If we want to find a preimage of some x, and we find a preimage of which is not exactly a preimage but some close thing, then we see what is the difference and try to find the difference by adding some vector and looking at the derivative. Of course, for complexity there is no such thing as a derivative, but maybe still theoretically, since the homotopy also has no relation to complexity, maybe this can be also somehow applied, and in this way we can change quantities in a small, just adjust a bit in the end of the construction to get exact statement starting from less exact statement. But this is pure speculation. I have no idea how it works or whether it's possible at all, but maybe I just want to mention this possibility. Maybe somebody can do this. Okay, so that's all.
We have time for a quick question. What do you know about the monotone case for the monotone complex?
Oh, if we are in this argument, we can do whatever we want because they are all closed. So and they are all, but they are not continuous. Oh, yep. Then changing complexity in the condition, if we want the condition to be monotone, it's another story. But maybe you can try to have a prefix-free set of conditions, look among them. So I think it's not very interesting.
The argument is working or not?
I think it should. But we need to be careful. So, for example, we can look for y and in some prefix-free set. So small changes won't change it too much. But okay, I'm not sure really whether it works or not. But
it seems that the topological argument, the numbers don't have to be the same exactly. Right?
yeah,
So
unlike the Muchnik case, the numbers can be different.
Would that work with the game also give you?
That's another open question. How to actually you need a different game because you don't. It's no hope to make a one-to-one correspondence because the average number of partners should be more or less the same on both sides. It's the standard problem for statistics. when it's not the same, but still, but we need multiple kind of grafted bounded degree instead.
Okay, let's thank the speaker again.